The macro also configures FRF12 frame relay fragmentation and interleaving in the map class. The purpose of this feature is to break up data packets so that voice packets do not have to wait for a long data packet to be serialized onto the link. We can see how the fragment size was chosen by examining the shaping parameters on R1. Note that the fragment size is 320 bytes. This is equal to our byte limit with our interval of 10 milliseconds. By chopping up data packets into 320 byte fragments, each fragment can be transmitted within our 10 millisecond interval. If a large data packet gets in front of a voice packet, FRF12 fragmentation and interleaving will send just the first 320 bytes of the data packet, then it will send the voice packet. The rest of the data packet will then follow. Without fragmentation, a voice packet could wait up to 50 milliseconds for a 1500 byte data packet to be transmitted at the 256K rate. This would waste a third of the total end-to-end delay budget for the voice packet. Next, we'll take a look at the policy map that was created by the AutoQoS macro. Let's see how it was configured on the router. Here you see the class maps and the policy map called AutoQoS Policy Trust. This policy was applied to the shaping queue by using the service policy output command in the map class. It creates a priority queue for the voice data, which is identified by the class AutoQoS Voice over IP RTP Trust, as you see here. This class simply matches all traffic marked with Differentiated Services Code Point value EF, which stands for Expedited Forwarding. Cisco phones automatically mark all their voice traffic with this DSCP value. Because this traffic is put in a priority queue, the voice packets will get sent to the interface before any other type of traffic. The class AutoQoS Voice over IP Control reserves 5% of the bandwidth in the shaping queue for voice control traffic. Voice control protocols include SIP, MGCP, and H323. Cisco phones mark this traffic with DSCP-CS3 or AF31. All other types of traffic will fall into class default. The macro has implemented weighted fair queuing for this traffic. Let's see how these policies look on our router. Here you see that our voice traffic is defined in the class map. Traffic matches DSCP-EF, which is decimal value 46. It is being placed in a priority queue using up to 70% of the bandwidth. Note that 70% is a percentage of the min CIR, not the CIR. If the macro had not set the min CIR to 256K, it would have defaulted to only half that. As a result, only 89K would have been reserved for the priority queue instead of 179. To summarize, the AutoQoS Voice over IP macro automatically optimizes your frame relay connection to support voice over IP traffic. All we have to do is configure a point-to-point subinterface, properly set the bandwidth, and enter the macro in DELC configuration mode. When we use the trust keyword, it is assumed that all traffic marked DSCP-EF is voice traffic. It is put in a priority queue, compressed, and goes out the interface first. Voice signaling traffic is assumed to be marked CS3 or AF31. If the queue becomes congested, up to 5% of the bandwidth will be reserved for it. Data traffic has the lowest priority. It will be fragmented if necessary so as not to slow down the voice packet. Cisco IOS provides 3 sets of tools for frame relay traffic shaping. These techniques are often referred to as GTS, FRTS, and class-based. This presentation focuses on the fundamentals of FRTS. We cover class-based shaping and shaping for voice QoS in later presentations. Most frame relay networks will implement frame relay traffic shaping to meet one or more of the goals you see here. Mismatched access rates can lead to very poor network performance over frame relay. For example, if a headquarters site has a T3 connection to the frame cloud, it may attempt to send traffic up to 44 megabits per second over any given PVC. If a branch router on the other end of that PVC has only a T1 access rate, then most of that traffic is going to be dropped. This condition is called egress blocking. We will see how FRTS can help us here. Alternatively, it may happen that both routers have the same T3 access rate, but the PVC between them is only T1. If the ISP is strictly enforcing the PVC rate, then it will drop the excess. FRTS can also help us here. By default, only physical interfaces have manageable queues. Subinterfaces and DELCs must share it. FRTS creates a 40-packet queue per PVC, which can be managed to guarantee bandwidth and create a priority queue. FRTS also enables advanced fragmentation features that can help reduce delay and jitter. As we will see in a later presentation, these features of FRTS are critical to supporting voice over IP traffic over frame relay. The effectiveness of traffic shaping relies on the fact that most network traffic is bursty. The rate of traffic on an interface is usually not constant, but varies around the mean value. Traffic shaping is an attempt to save traffic in a buffer during the peaks and then send it when the rate is low. There are important practical limits to this technique. One is the size of the buffer. Each stored packet requires RAM, and RAM is a limited resource. A related problem is that of acceptable delay. While these packets are being stored on the sending router, an application at the destination is waiting for them. Some applications are more sensitive than others to delay. FTP can tolerate a lot more delay than can voice over IP. Buffering can also lead to jitter, which is variability in delay. The three methods of shaping traffic over frame relay links offer various strengths and weaknesses. Generic traffic shaping uses the traffic shape command on the interface. One advantage of GTS is its ability to shape a subset of traffic defined in an access list. Another advantage is its relative simplicity. FRTS requires that we enter the command frame relay traffic shaping on the physical interface. It has been widely used for many years and has a fragmentation technique, FRF12, that is useful for voice over IP. On the downside, FRTS shapes all traffic on all DELCs with default parameters. As we'll see, default shaping values are changed by creating a map class and applying it to individual PVCs. Class-based shaping is the newest of these toolsets. It can be applied at the interface, subinterface, and PVC level. Class-based shaping allows us to shape complex subsets of traffic in powerful ways. Let's see how we can use a simple FRTS configuration to save us from an access rate mismatch problem. The hub router, R1 in our scenario, is configured with a T3 link to the provider, and the remote office, R2, is connected by just a T1. Users are complaining of poor network performance, yet average utilization of the T1 is reasonable. The problem may be that large bursts of traffic are being sent by the hub and dropped by the provider switch connected to the T1. To address this, we will try to shape the traffic coming out of the hub router to T1, a rate the branch link can handle. Here is how we create and apply it on R1. First, we create a map class frame relay in global configuration mode. Here we set the CIR to T1, our target rate. We will try to buffer any traffic over this rate and send it when the peak subsides. Next, we must activate frame relay traffic shaping on the physical interface. Finally, we go into the subinterface and apply the map class to the DELC using the class command. We use the command show traffic shape to give us a quick view of the shaping parameters. Note PVC 102 has our target rate. The byte limit and interval are critical features of FRTS. The physical interface can only send traffic at one rate, T3 in our example. To get the interface to send at a T1 rate, FRTS doles out the traffic to the interface at the rate of 6,144 bytes every 32 milliseconds. If PVC 102 traffic is the only traffic on the interface, then it will send 6144 bytes at a T3 rate, then wait until the next 32 millisecond interval and send another 6144 bytes. This will happen 32 times until the interface has sent a total of 1,536,000 bits, or 192,000 bytes, in 1 second. The byte limit and interval are calculated automatically by the router based on the CIR. The table you see here gives these values for some other rates. Note, by the way, that PVC 103 is being shaped to a rate of 56K. Forgetting that FRTS applies this rate to all PVCs by default could be a career-limiting move. Let's create a map class that demonstrates some of the power of FRTS. Imagine the same hub and remote offices, but now we have only a 384K PVC between them. As long as the network is not busy, our provider lets us send up to 512K. When the provider network does get congested, it marks traffic over the PVC rate as discard eligible and signals us to throttle back by having the beckon bit set in return traffic. In the past, we found that we can usually get away with sending at a T1 rate for short periods.